Hi, welcome to Macrocircuits, where we study architectures in brains and machines. My name is Surya Ganguly, and I'll be giving you this lecture today. So just before we get started, sort of what's the big picture of learning, both in brains and machines, and how does everything fit together? Well, first, we'd like to understand how the structure of data, the architecture, and the loss function conspire to determine the shape of the error landscape. So for example, this could be the error as a function of the weights. Initialization hopefully starts in a favorable part of the landscape, and then the learning dynamics forces the neural network to get better and better to lower error, and hopefully the lower training error, but hopefully the endpoint of learning also has low test error, i.e. the network exhibits generalization, potentially due to inductive biases in the learning dynamics. And eventually we'd like to also understand what the learned representation is doing, i.e. this is sort of the province of explainable AI. If you're interested in sort of an overview of this kind of picture, you can take a look at this review article here. Okay, so there's a variety of macro architectures at our disposal. For example, convolutional neural networks, which build in translational equivariance in images. A vision transformer, which could do things quite differently. And for example, a recurrent neural network that specializes to processing time series. And so why might we want to choose one architecture or another? Well, there's a couple of theoretical questions that might guide our design, guide our choice of architecture and designs of architecture. The first question is, what functions can a given architecture efficiently express? This is known as the expressivity problem. And how well can architecture plus initialization and learning dynamics help generalization with limited training data? These are two kind of key questions that we'd like to talk about today. There's an interesting result called the universal approximation theorem, which says that shallow networks can actually say it all, right? So here's the basic idea. Let phi be any sort of continuous activation function that's not just a simple polynomial. Let f be a continuous target function. This is the kind of the true function that you want to try to learn, right? Let g of x be a family of neural network functions that correspond to a shallow neural network. So here's x. Here's g of x. There might be, say, a bunch of ReLU units here, and they combine with incoming and outgoing weights to construct g of x, right? And the universal approximation theorem says that for any compact subset of the input, and for every error tolerance level epsilon, there exists some integer n, where n is the number of hidden units, and a set of parameters, which is incoming and outgoing weights and biases, such that the corresponding function, g of x, is close to the target function to within an error tolerance epsilon over the compact set k. Okay, so this sounds fantastic, right? I can approximate any continuous function with just a shallow neural network. So why do we even need deep neural networks? Okay, well, there's something a little bit hokey about the universal approximation theorem. It doesn't tell us how many hidden neurons we need. The key condition is there exists an integer n and a set of parameters such that g of x can get close to f of x within epsilon. It doesn't tell you how n scales with the complexity of the target function f or epsilon or anything like that. It could be that you need a huge network if it's shallow, okay? So this leads to the question of, what are scenarios in which we might need deep networks? For example, there might exist some functions which can be efficiently approximated by a deep network, where efficient might be a polynomial number of hidden units in, say, the input dimension of the problem. But to approximate these same functions with a one hidden layer network, you might need exponentially more neurons. Okay, what's a generic class of such target functions? It turns out any random deep network in a so-called chaotic phase gives you such a function. And such a function is exponentially curved in depth. So what do I mean by in a chaotic phase? Let's say the weights of the neural network are large. So two nearby inputs through the large linear weights will be expanded and become further apart from each other. But then let's say the nonlinearity could be, say, a sigmoidal nonlinearity that folds input space. So then through the nonlinear folding, the two inputs become closer, but then in the next layer, they expand due to linear expansion and become closer. So two nearby data points will actually become quite far apart through this iterative procedure. And inputs will become sort of exponentially curved. Here's an example of, for example, a very simple shape in the input space, in, say, layer 0. and it propagates to layer 2, to layer 4, to layer 6, to layer 8, and you can see it becomes more and more curved as it propagates through a deep network in the chaotic phase. Okay, if you want to learn more about this, you can see this paper here that we wrote a while ago, but you'll actually explore this in tutorial 1, where you'll explore networks in the chaotic and ordered phase. Now, it turns out if you have a deep network in the chaotic phase, that's a very generic class of examples where to express such a highly curved or exponentially curved function, a shallow net would require exponentially more neurons than the deep net. So this shows that there's many, many functions that can be efficiently implemented by a deep network, but not efficiently implemented by a shallow network. And the interesting question is, the functions that we care about in human learning, are they of that form? They likely are, right? Because we are not shallow networks. Okay, so now the issue of generalization, okay? There's a very important theorem called the no free lunch theorem. So let me explain that now. So it turns out any learning algorithm, which you can think of as an architecture plus a learning rule that sets the weights of the architecture given the training data. Okay, so if you think of a learning algorithm in this general way, the no free lunch theorem says that when performance is averaged over all possible tasks, every learning algorithm does equally well. So for example, if you think of this horizontal axis as the space of tasks, and this is performance, right? Learning algorithm A might do pretty well on this set of tasks, at least better than algorithm B. But if you average over the tasks, they have the same performance, which means that there must exist a different set of tasks where algorithm A does worse than algorithm B. This automatically means that there is no magical algorithm or no magical optimal algorithm C that dominates all other algorithms and all other tasks, right? This would have a performance characteristic that would be up here, and its average across all tasks would be different from the average across these two curves, right? So if algorithm A does better than B on a set of tasks, there must exist other tasks where A does worse than B. So this tells you automatically that to perform well, we must tune the architecture and learning rule to the structure of the set of tasks we want to solve. And the million-dollar question is, what is the nature of the tasks that human beings solve? And then what kinds of architectures are good at solving those types of tasks? Of course, we know there are other tasks that human beings are terrible at, like multi-digit multiplication, for example, and we can use calculators to do that. Okay, if you're interested in elementary proof of this, you can take a look at this excellent book here. Okay. Now, in terms of macro architecture, if we think about what are the properties of macro architectures at work, the most salient development in AI has been sort of Richard Sutton's bitter lesson. The more compute and the more parameters and the more data, the better you do, right? Now, it turns out, interestingly, that the number of parameters can sometimes exceed the amount of data, and you're still fine. How is this possible? This is quite a surprise, because classical learning theory says that the test error will be less than the training error plus some measure of the complexity of the architecture divided by the number of training data points that you have. This is what classic learning theory tells you. Examples of the complexity of the architecture could be things like the VC dimension or the Rademacher complexity. But roughly, you can think of the complexity architecture as the number of parameters for typical neural networks, right? So when the number of parameters is much, much bigger than the number of data points, this yields a completely vacuous bound, right? Test error is a probability. This would say that the probability of the test error is less than the probability of the training error, plus some number that's bigger than 1, right? This is a totally useless bound, right? So this raises the question, why do overparameterized architectures still generalize? This puzzle was raised in this well-known paper here, okay? And this book covers the classic learning theory. Okay, the basic idea is that this bound, while correct, doesn't capture everything that's going on when we're learning. It turns out learning is better characterized by a dynamic procedure. So here's a kind of a cartoon picture of why you might generalize well despite having so many parameters. So let's say that you have a huge parameter space, right? And let's say this space is the space of weights of the neural network. Now, if there's not that many training data points, this means that there'll be a huge volume in weight space that has 0 training error, right? There'll be many, many weight configurations that get you zero training error. Now, many points in the space, they all have zero training error, but they might have really high test error, right? But if you start your gradient descent from a very simple initialization, for example, all the weights close to zero, and then you do gradient descent starting from the simple initialization, you'll get to a simple point in the space of zero training error solutions and ultimately get to a simple function. Hopefully, that's the hope. And this special point that gradient descent gets to you to starting from initial condition might have good generalization. Of course, if you start from really, really large weights, for example, in the chaotic regime, the regime that you'll explore in tutorial 1, you might descend using gradient descent to a very different point in the zero space of zero training error solutions. And that might get you bad generalization error, right? So you're going to explore this in your next tutorial. In tutorial 2, you're going to explore how does the scale of the initialization, noise in the training data, and potentially explicit regularization impact generalization error as a function of the number of parameters. And you'll explore one of the most famous recent results in machine learning, which kind of overturns classical wisdom about how generalization error behaves. So we're used to this part of the curve. So this is the number of parameters in your model. This is the error, either train or test. We're used to the training error dropping as you add more parameters. And the test error might go down, but then you start overfitting and the test error goes up, right? But then at a certain point, you become over-parameterized. You have more parameters than you need. So right when you have the exact number of parameters needed to fit the training data, that's considered the interpolation threshold. And then there's only one point in weight space that gets you zero training error. But as you move beyond the interpolation threshold, you get a larger and larger volume in weight space. And as long as you start from a small initialization, you can get smaller and smaller test error, actually. And then you're back to this kind of picture here, right? The over-parameterized regime is where this circle is big and gets bigger and bigger as you move along this axis, right? So you'll explore numerically in a very simple setting of one hidden layer networks trying to mimic a sine function, how you get this behavior. And the most important thing to take away is generalization error can decrease with model size if starting from a small initialization, even without explicit regularization. So this is an implicit bias of stochastic gradient descent towards simpler networks. This theory can get a lot more sophisticated, actually. In a recent paper, we found an interesting result where any accurate Langevin dynamics model of stochastic gradient descent, where you model stochastic gradient descent by a drift term which goes down the full batch gradient, and a diffusion term that takes into account mini batch noise, that descent must have a position-dependent diffusion tensor because the diffusion tensor mimics the covariance matrix of gradients across mini batches, and that depends on where you are in weight space. We showed that this tensor vanishes at saddle points of enhanced symmetry with many identical neurons. And this vanishing diffusion actually attracts SGD to saddle points where there might be some negative curvature directions and positive curvature directions at a point where the gradient vanishes, as opposed to local minima, which have only all positive curvature directions. We used to think that gradient descent, stochastic gradient descent would stop at local minima, but this shows that it stops at saddle points. And even though these saddle points have higher training error than the local minima, we can show, both theoretically and experimentally, that these saddle points actually have superior generalization performance. They have better test error. And the reason is these saddle points correspond to networks with many, many identical neurons with identical incoming and outgoing weights. So these are highly redundant networks. And so this suggests that deep learning has far fewer effective degrees of freedom than naive parameter counts might suggest, right? So even though these networks are over-parameterized, they don't use all of these parameters. They end up at points where you have many, many neurons with identical incoming and outgoing weights. And we can show that in experiments. So if you're interested, you can take a look at our recent paper here. Okay, now let's go. So that's kind of a big picture of what we know about the theory of macro architecture, which is not that much, actually. But let's move on to biological versus artificial intelligence. So, the last decade has led to remarkable engineering advances in AI with remarkable capabilities that we don't understand fully. But of course, over 500 million years of vertebrate brain evolution has also culminated in the human brain and the brains of many interesting mammals, that are also quite remarkable and can still do things that are many, many orders of magnitude better than AI systems. So what are major order of magnitude discrepancies between current AI and biological intelligence? Here's a few. One is data hungriness. For example, if GPT-3 read at the same rate as humans read, then it would take about 20,000 years to ingest all its pre-training data, right? Energy hungriness. Our brain spends 20 watts, but AI is in the megawatt range, and people are now talking about gigawatt data centers and even talking about building nuclear power plants to power AI, right? You don't need a nuclear power plant to power yourself, so you're much more energy efficient. Lack of robustness. For example, adversarial examples, they haven't gone away, right? AI systems make foolish mistakes that humans would never, ever make, right? Deep logic and reasoning where you need to take many, many deductive steps. AI cannot do this, but we can, right? So there's many, many orders of magnitude discrepancies between AI and biological intelligence still, despite the remarkable capabilities of AI. So let's go through some potential reasons for these discrepancies. And they lie, I think, in macro architecture. So what are huge differences in the architecture and properties of brains and machines, right? There's lots more in heaven and earth than there are dreamt of in our GPUs, in some sense. What are some examples? The way we model synapses might be one example. We model a synapse from neuron J to neuron I as just a number, Wij, denoting like how much neuron I fires in proportion to how much neuron J fires, right? But biological neural networks, individual synapses are entire molecular dynamical systems of their own right. For example, this is a phosphorylation-dephosphorylation network of kinases and phosphatases hiding inside the postsynaptic density of every single pyramidal neuron, right, in your brain. So it's a very, very complicated machine, right? There's ideas for how this machine might play a functional role. One example is metaplasticity, where whether or not a synapse potentiates or depressed, gets stronger or weaker, depends on the history of past events, right? Here's a nice review on that. What are some uses of this metaplasticity? One is rapid learning and slow forgetting, right? So for example, there's a trade-off between learning and forgetting. If you learn rapidly, then you'll keep overwriting old memories with new memories, and then you'll also forget rapidly. One way to solve that is maybe to learn slowly, but then of course you'll forget slowly, but you also learn slowly. So how do you get both rapid learning and slow forgetting? All right, so in this couple of papers, they propose these complex metaplastic synapses that could do that, and you can look at the details there. Also, continual learning, right? As we learn new tasks, we don't forget our old tasks, right? But AI systems tend to have problems with that. So in a paper that we wrote a while ago, we showed that these complex synapses could allow continual learning where new tasks don't overwrite old tasks. And the key idea is to have the synapse be a dynamical system where each synapse maintains a notion of how important it is for learning previous tasks, and the important synapses slow down their learning rate, and the unimportant ones are free to learn new tasks. And then you don't get this catastrophic forgetting. You can learn new tasks without forgetting old tasks. All right? Modules, right? The brain isn't just one undifferentiated big transformer, right? The brain has many, many different regions, each with different microcircuit architecture, each with different learning rules, and they all talk to each other with poorly understood communication patterns. Here's an old article by Kenji Doya where he had an interesting hypothesis that, for example, the cortex does unsupervised learning, the basal ganglia does reinforcement learning, and the cerebellum does supervised learning. The picture's probably a bit more complicated than that, but it's a really intriguing idea that we need to think about this differentiation of regions into different types of learning machines. Here's a more fine-grained version of that, where here they looked at hierarchical control in the motor system and top-down feedback in the sensory system. These are two great review articles to learn about the modular structure of motor and sensory systems. Okay. Here's one more concrete example of nested feedback loops as a principal design motif in control circuits in the brain. So for example, if you think about the control of your arm, there are these nested feedback loops where you have fast, dumb subcortical loops that can correct any perturbation away from the correct trajectory, right? They implement reflexes. So if you're reaching somewhere and somebody hits your arm, your fast, dumb cortical loop will immediately oppose whatever direction somebody moved your arm, right? But then there's slower, smarter cortical loops that will correct motor perturbations to your arm only along directions that are relevant to task goals and not along directions that are irrelevant to task goals. So the deeper loops know about what your goals are, the reflexes don't, right? If you're interested, here's a great set of articles to learn more about this, okay? So in your tutorial 3, what you're going to do is you're going to see how modularity can speed up learning and improve generalization. So for example, you're going to look at a task where the goal is to navigate to a remembered target. And so you're going to explore a modular agent with 3 macrocircuits, a recurrent neural network to integrate sensory inputs to estimate the state of the navigating agent, where it is, and the state of the environment, where the target is in relation, where the remembered target is in relation to the agent. You'll have an MLP module that will select actions, and you'll have another MLP module to compute the value of actions through reinforcement learning. You'll compare this agent to a non-modular agent that's just a big undifferentiated neural network. And you'll find out that the modular agent, in comparison to the non-modular agent, actually learns the task faster and it generalizes better to novel but related tasks. Right? So I think one of the big mysteries of the brain is, why did evolution choose the modular structure that it chose? And I think there's a lot of research to do to try to figure that out. This is kind of a really nice toy problem in which to start to analyze or think about that. Okay, in memory, there are also different modular systems as well. For example, you have your hippocampus, which are fast memory circuits that store your episodic memories of that are basically memories of individual events, like who, what, when, where. For example, what did you eat for breakfast this morning? You need your hippocampus to remember that later in the day. But over longer times, these memories are abstracted away and transformed to cortex, transferred to cortex. And then that's where you sort of have your semantic memories, general knowledge, for example, facts like birds have feathers. You probably don't remember when was the first time you learned that birds have feathers. That was a particular episode. Maybe your parents or a teacher taught you that. But those details have been abstracted away, and you just know that birds have feathers, right? So here are some nice articles to learn about these complementary learning systems theory. Also, a key important thing to note is that, we're not just passive feed-forward networks. We're engaged continually in an action perception loop, right? Where sensory inputs propagate into the brain, we make decisions. Those actions affect what we see next, and so you have this. You have the sensory consequences of your current motor commands. And, imagination and planning involve simulating the sensory motor loop into the future to imagine possible futures contingent upon different actions. And then we can choose actions now based on imagination. And so you have planning and so forth. So I don't think we have a really good understanding of how to learn these sensory motor loops and do active learning and active perception and so forth. So this is a really interesting direction for future research. Active learning in general, the baby is a scientist. So there's a really nice experiment where, for example, let's say you show a baby a movie where in the movie there's a magical object A that doesn't fall when dropped and a magical object B that can go through walls. Then the baby's actually given real-world versions of object A and object B. They're not magical anymore. They're actual objects in the real world. So how does the baby play with them? It does so in a very interesting way. Object A, it throws it over the high chair to see if it will actually fall if it drops it, right? But magical object B, it will bang it on its high chair to see if it will go through a wall or go through a solid object. So it plays with these two objects in very, very different ways. So this suggests that the baby is continuously building internal models of how the world evolves over time. It pays a special attention to events that violate their world model. For example, an object not falling or an object that can go through walls. Then it performs active experiments to gather its own data, and it updates its world model as it does its experiments. So babies are not passively ingesting data like GPT-3. They're doing active experiments. They're asking through curiosity-driven play for new training data, right? And I think this is a really interesting difference between brains and machines. Okay, energy in brains and machines, right? How do we build more energy-efficient AI systems, right? So, for example, most power in today's machines are consumed in wires, not in computation, because a lot of energy is consumed in just shuttling electrons around between computing elements or moving data from memory to the GPU, right? So to reduce power, we must make wires shorter, but it's hard to make wires shorter in 2D, so we'd like to build chips in 3D, right? But building chips in 3D poses a problem. Power consumption grows with volume, but the rate of heat dissipation can only grow with the surface area. So as you make the chips bigger, it consumes more power, but it can't dissipate the power through the surface area, right? But brains have solved the heat dissipation problem, right? Brains have solved the heat dissipation problem. So how do they do it? It turns out there are beautiful scaling laws, and you can learn about them, for example, in this book, that show that as brains get bigger, their activity patterns get sparser, and the surface area increases through folding. So then the power consumption grows sublinearly in the volume, and the surface area kind of grows superlinear in the volume, so that everything matches up. And so my colleague Kwabena Bohannon wrote about this in this Nature article and proposed ways to build 3D chips inspired by the way that the brain solved the problem of 3D computing. Right? Also, why does the AI spend megawatts and the brain spends 20 watts, right? I think the problem is actually with digital computation itself. We decided to compute using fast and reliable bit flips by shuttling lots and lots of electrons around through transistors. Every fast and reliable bit flip requires a huge energy expenditure, which is demanded by the laws of thermodynamics. But brains are mixed, analog, digital, and noisy. The intermediate steps are slow, they're unreliable, but the final answer is just good enough. So biological systems look quite messy and unreliable, but this is the secret of their energy-efficient biological design. And so recently we've been thinking about what are the fundamental limits on the speed and accuracy of computations given an energy budget. And we've been combining information theory and statistical mechanics to derive these fundamental limits. If you're interested, you can take a look at this paper in the context of cellular sensing. But I think there's lots of interesting work to do to understand energy, speed, accuracy, and computation. Okay, just to summarize, we have these 10 years of engineering advances, but the brain has 500 million years of vertebrate brain evolution underlying it. Interestingly, we have zero engineering design principles to explain how a complex sensing, communication, control, computing, and energy distribution network like the brain can continuously scale up over 500 million years through this great chain of being going from us to, lowly worms without ever losing function, right? And so we have a lot to learn about brain macroarchitecture and properties to develop more data-efficient, energy-efficient, and robust AI capable, for example, of deep logical reasoning. And so I hope this inspires you to go out and attack some of these problems. We need a lot of help here. Thanks.